Good afternoon, dear Chairman, dear participants. Let me introduce myself to you. I'm Daria Fedotova. I'm a postgraduate student of Kazan Scientific Center of Russian Academy of Sciences. My co-authors are Professor Valery Shlyannikov and Ruslan Khamidullin. The title of my talk is Couple Analysis of Digital Image Correlation and Finite Element Method to Quantify Strand Fields and Correct Plane Displacement in Structural Materials under Cyclic Mixed Mode 1 and 2 fracture. Outline of my talk is the following. First will be given introduction, then is specimens, test equipment. The next part is material properties and experimental crack paths. The following section is the numerical results, strain gradient plasticity theories. After that, we'll look on analysis of the crack tip under mixed mode fracture by digital image correlation and finite element method. And finally, we'll be given conclusions. The subject of the numerical and experimental study is a compact tension shear specimen, CTS specimen. The test setup included a servo-hydraulic test frame with a control system. The mixed mode cyclic fracture tests were performed at a frequency of 10 Hz at a load ratio equal 0.1 with discrete applied force direction. CTS specimens in S-shaped grips are presented here, as well as the Wick-Friede complex, which was used to measure and fix the displacement field at the correct tip of CTS specimens by the digital image correlation. The figures show the tested compact tension shear specimens, pure mode 1 and initial mode 2. All compact tension shear specimens produced from two type steels, titanium and aluminum alloys. Specimen sizes, loading conditions, and main mechanical properties all tested materials are listed in tables on slide. As a result of the tests, experimental crack paths were obtained based on periodically measured increments of crack length in initial mode 2 loaded CTS specimens for all the materials we are considering. The numerical analysis. The modeling of the calculation schemes was carried out in accordance with the geometric parameters of the experimental CTS samples by the commercial finite element software package and SIS. Numerical calculations were performed using the experimental set of forces for each tested specimen manufactured from two types steel, aluminum, and titanium alloys. Typical finite element meshes for the experimental crack path and crack tip area in the CTS specimen are illustrated in the upper figures. The elastic plastic analysis was based on two theories of plasticity. The first of which is the classical Hutchinson-Rice-Rosengren model, and the other corresponds to the strain gradient plasticity theory. In our study, we used conventional mechanism-based strain gradient plasticity theory. This conventional theory based on the Taylor dislocation model with accounting for the geometrically necessary dislocations and the statistically stored dislocations. A wide range of intrinsic material length parameter values was used in numerical calculations. The range is from 1 to 10 microns. Consider the numerical results. The comparison of radial distributions in the densities, geometrically necessary dislocations, and statistically stored dislocations for steels, aluminum, and titanium alloys are shown in figures as a function of the crack tip position along curvilinear crack paths. The obtained results are expressed as a function of the normalized crack tip distances by the intrinsic material length parameter. The first two figures are related to pure mode 1 and initial pure mode 2. Next pictures represent point 2 that correspond to an increment in the crack length of 2 mm at the moment of kink of the crack, and point 7 correspond to the state before the final fracture. The geometrically necessary dislocation density is large around the crack tip, but rapidly decreases away from it. In contrast, the statistically stored dislocation density is not as large as that of geometrically necessary dislocation around the crack tip, but decreases much more slowly away from it. The contour plots for dislocation densities are shown in figures for pure mode 1, pure mode 2, and mixed mode loading conditions. Figures illustrate the typical shapes and sizes of the respective contour plots of diametrically necessary dislocations and statistically stored dislocation densities formed by the loadings of mode 1 and initial mode 2 based on the strain gradient plasticity theory. The next slide compares the behavior of the effective normalized stresses on crack extension for the two theories of plasticity for several successive positions of the crack tip on a curved path of its growth. One of them is the strain gradient plasticity theory, and the other corresponds to the classical Hutchinson-Rice-Rosengren model. On these graphs, the effective stresses on the crack extension under gradient plasticity are an order of magnitude higher than under the classical HRR theory of plasticity. As moving away from the crack tip, the effects of gradient plasticity disappear, and the solution gradually moves to the state of a classical singularity of the Hutchinson-Rice-Rosengren model. The bottom row of figures demonstrates the behavior of plastic zones at the crack tip according to the strain gradient plasticity theory solution. Figures show a contour of the plastic zones for titanium alloy for pure mode 1 as well as for the initial mode 2 and 2 point of the crack growth path. I would like to draw your attention to the fact that as the crack grows, the shape of the plastic zone gradually changes from pure mode 2 to a state close to mode 1. Let's denote the pseudo mode 1 scenario. The next slide presents an analysis of the singularity exponent behavior for asymptotic models of the crack tip stress fields for different loading conditions. 3 different domains surrounding the crack tip can be identified as a function of asymptotic stress fields. The value of the crack tip singularity was necessary for calculating the elastic plastic stress intensity factors according to the strain gradient plasticity theory. The sensitivity crack tip singularity to material structure scale parameter can be seen by the values at the selected points. Note that as the crack grows under pure mode 2 conditions, we again observe the phenomenon of pseudo mode 1 scenario. Next figure shows a comparison of the numerical distributions for the equivalent elastic stress intensity factors, plastic stress intensity factors according to the classical and strain gradient plasticity theories for each of the experimental crack paths in the CTS specimens for the studied steels and titanium and aluminum alloys. The left row of figures shows the stress intensity factor distributions as a function of the normalized crack length for pure mode 1, while the right row corresponds to the initial pure mode 2 with subsequent cyclic mixed mode fracture. Figures clearly illustrate the influence of the plastic properties of materials on the dependence of the elastic and plastic stress intensity factors on the crack length using the example of pure mode 1. As for the distribution of plastic stress intensity factors for the two theories under consideration, we will analyze additionally. Let us consider the distributions of the new stress intensity factors according to the strain gradient plasticity theory for all investigated materials and all loading conditions in the range of values of the scale parameter. The main advantage of the new stress intensity factors according to the strain gradient plasticity theory in comparison with the classical plastic stress intensity factors is its sensitivity to changes in the material structure scale parameter. Analysis of the crack tip under mixed mode fracture by digital image correlation and finite element method. This slide shows the results for steel. It's pure mode 1 loading conditions. This is the first point along the considered path. Here are the deformation fields at the correct tip. The first contours were obtained during the testing of CTS specimens using the weak 3D complex. The video shows a recording of one loading cycle. The lower figures correspond to the result of numerical calculations of finite element method in the framework of classical and gradient theories of plasticity. All results are presented in a single range of values. As we can see, visually the shapes of the contour of the deformation fields are identical to each other. On the right are the distributions of deformation along the crack extension obtained using weak 3D, as well as calculated by finite element method. I would like to draw your attention to the fact that our results relate to the field of nonlinearity. Here we observe a significantly plastic state, where the stresses in the crack tip area are several times higher than the yield strength. Next, consider the state of the initial mode 2. Here, the shapes of the deformation contour have already changed. The data from the weak 3D complex and the finite element method correspond to the initial mode 2. As for the area of the continuation of the crack, the stress values are in the plastic zone. In conclusion, I will present data for steel in mixed mode. The crack length is 28 mm. The video also shows one loading cycle. The contours of the deformation zones at the crack tip and the distribution of deformation on the continuation have the same features as at the first point. In addition, we have obtained experimental proof of the presence of the pseudo-mode 1 scenario. Conclusions. Series of tests for CTS specimens under pure mode 1, mode 2, and subsequent mixed mode was carried out. As a result of the experiments, curvilinear crack paths for samples made of steels, titanium, and aluminum alloys were obtained. Next. Numerical analysis for experimental crack paths of the tested materials shown the differences between effective dimensionless stresses according to classical HRR and SDP theories are approximately about 1 order of magnitude. Nonlinear stress intensity factor solutions for classical HRR plasticity and strain gradient plasticity for different experimental crack paths are determined. It is found that the main advantage of the new stress intensity factor, according to the gradient theory of plasticity, is sensitivity to changes in the material structure scale parameter. And in the end, by comparing the experimental and numerical data, the areas of mutual correspondence of their plastic stress distributions obtained by digital image correlation and the finite element method are established. Thank you for your attention.